until this point, we've made one assumption of all the objects we've seen so far, that they are point-like. It turns out that for many situations in the real world, this is a perfectly valid assumption. It can be shown that every object behaves as if all its mass were concentrated at a single location, which we call the center of mass. For instance, if a hammer is thrown, there is no mathematical difference between calculating the weight force at every point in the hammer versus pretending that the weight force acts at only the location of its center of mass. Even if the rest of the motion of the hammer is very complex, the motion of the center of mass will be given by the simple equations that we have seen so far in this semester. So the concept of center of mass significantly simplifies our calculations, but there are two other reasons why center of mass matters. One we will see at the end of this video, and another we will see in a few videos from now. For now, let's see how to calculate center of mass. The center of mass is a position. We've treated all objects so far as being single points, so the object and the center of mass have always been the same thing so far. But what if you had multiple objects? For instance, here we see 3 asteroids in space. Their masses are shown inside each asteroid, and they are located at the coordinates shown. Where is the center of mass? The center of mass is determined by this equation, assuming that you have discrete particles. For each asteroid, take its location, that is its x-coordinate, multiply by the mass, then add all of those products up, and finally divide by the total mass. That's easy enough. When we solve this, we get the center of mass being 6.57 I. So the center of mass is located somewhere between the 5 kilogram asteroid and the 7 kilogram asteroid. Now you'll notice that this center of mass actually doesn't correspond to any particular asteroid by itself. It's somewhere between 2 asteroids. That is completely legal. Now, what would happen if the asteroids were not all in a straight line? In this case, the center of mass will not lie along the x-axis. It will have a y component as well. In this case, we have to apply the same equation as before, but we have to do it twice, once in the x direction and a second time in the y direction. When we do the calculation in the x direction, we get the x-coordinate of the center of mass, 6.57 I hat. When we do it in the y direction, we get the y-coordinate of the center of mass, 1.93 j hat. So the location of the center of mass is 6.57 I hat plus 1.93 j hat. So far, we have looked at point masses. But what happens if we have an extended or a continuous object? Here, we see a cylindrical rod made of iron. Its length is 6 meters and it has a cross-section area of 0.1 meters squared. Iron has a density of about 8,000 kilograms per cubic meter. Where is its center of mass? You might instinctively say that it is at the center of the rod, and you'd be right, but let's prove it. When we're dealing with extended objects or continuous objects, we have to use a different equation, one that uses integrals. I've written this at the right side of the screen. This is a little bit different from the way the book explains it, but it amounts to the same thing. Let's break down what it is saying. An integral is basically a glorified summation, and just like the summations we did in the earlier examples, when we take an integral, we are basically taking a large object like this rod and breaking it into very thin slices. Imagine the original iron rod was broken into many thin discs. I've shown a few of these slicings in the diagram, in the dashed lines in orange. Let's analyze one of these discs, picked at random, It's just shown here at orange down below. The thickness of this disk is symbolized as dx. The d represents the fact that the disk is very thin, and the x represents the fact that the slicing was done along the x-axis. Let's put in all the information that we know into this equation. The density is known, 8,000 kilograms per meter cubed, as is the area, 0.1 meters squared. We take these numbers and multiply by x to yield the integrand on top, and we do an ordinary multiplication to find the integrand on bottom. The limits of integration in both cases are the endpoints of the rod, in this case 0 and 6. Now we can integrate. The antiderivative of the top is 400x squared, and the antiderivative of the bottom is 800x. We evaluate these antiderivatives at the bounds 6 and 0 and subtract the lower bounds from the upper bounds. When we do this, we find the center of mass is located at 3 meters. Our intuition was correct. It was indeed at the center of the rod. Now, let's solve a similar puzzle for this square pyramid. The pyramid has a height of 10 meters. Each side of its base is 20 meters long, and it is made of a mysterious material that has a density of only 3 kilograms per cubic meter. Where is its center of mass? Based on the symmetry of the shape, you can probably guess that it has to lie somewhere below the tip of the pyramid. And again, you'd be right, but we still have to find the exact location. Take a slice from this pyramid as shown in the middle diagram. Each slice will have the same thickness, dy. However, the slices will have different areas. A slice taken closer to the tip will be a square with a small area, while one taken closer to the base will be a square with a large area. The area of each slice of each square depends on its side length. In fact, it is the side length squared. Since the side length decreases linearly from the base, where y equals 0 and the side length equals 20, to the tip, where y equals 10 and the side length is 0, we can work out a linear equation for the side length as a function of y. We see this in the third equation from the bottom. The side length for any height is equal to negative 2y plus 20. We square the side length to find the area of each slice, and then we use this in the center of mass formula. First, we will plug in all the information that is known. The density is known, as is the area as a function of y. We then multiply all the terms to determine what the integrands are. Simplifying, we get the integrands shown in the middle equation. From that point onwards, we perform the integral, and then we substitute the upper and lower bounds. This lets us solve for the center of mass. For a pyramid that is 10 meters tall, the center of mass is located at 2.5 j-hat meters. 2.5 meters above the base of the pyramid. Just as an exercise for yourself, look at the following collisions and point your finger to where the center of mass lies. As the objects move, the center of mass will move with them, so you need to keep moving your finger. But now here's something interesting. Even after the collision, your finger continues moving as it was before the collision. This applies to elastic collisions too. If you place your finger at the center of mass before the collision and keep moving it as the balls move, your finger moves in a straight line even after the collision. This brings us to a second important characteristic of the center of mass. In any collision, the center of mass always moves in a straight line. This video covered the concept and calculation of center of mass. In the next videos, we will see yet another reason why it is so important and how it ties into the next chapter in physics, which is rotation.